Good morning, students. Today, I decided to just give you a brief background to scalars and vector quantities, or simply scalars and vectors. Right, so welcome to the lesson. My name is Mr. Pochilola once again. Whether you are watching this lesson on YouTube or in a live classroom, today we will explore scalars and vectors. You are going to learn their definitions and importance in physics. You understand how they shape our understanding of the world as we go along. So feel free, jot down short notes, and please remember to channel questions if you have some to my number, which I believe you already have. But in case you don't have it, you can request it on the comment section. It is also pleasing that we have started special lessons for children with special needs, especially those with learning difficulties such as dyslexia. These can be taught by our expert team online, but we also have a team that is mobile, meaning that you can have lessons right at your doorstep, at your home. Okay, so children who cannot go to school due to challenges such as physical challenges can access education right at their doorstep at home. And all you have to do is contact us, and we are going to respond to you accordingly and arrange lessons. We have a vibrant team in Black Slides, which is always dedicated to helping people learn online. All right, so we welcome students from all walks of life, from all backgrounds, regardless of ethnicity, whether you are from Malawi, Zambia, even across Africa and beyond. All right, so welcome once again. Remember, if you are watching this video on YouTube, if you can manage, please like the video, share to other people who would also like to learn, and most importantly, subscribe to the channel so that you don't miss anything as videos are being uploaded. All right, thank you very much. So we are going to be looking at scalars and vectors, just an introduction. Yeah, this is just the introduction. Diving into scalar quantities. What are scalar quantities? All right, in physics, the word scalar, or the term scalar quantity, a scalar quantity is any physical quantity which has magnitude only. All right, so a scalar quantity is a quantity which has magnitude only. Scalars are defined by magnitude alone. All right, they lack directional properties. So we are saying a vector quantity is any quantity which is defined by magnitude only. Okay, so one property of scalar quantities Remember that quantities are the things you measure in the lab. Okay, so scalar quantities do not have direction. They are fully defined by magnitude. Remember, magnitude simply means size. A magnitude is just how big something is. Okay. So everyday examples of scalar quantities include mass, time, temperature, and others. Okay. Speed is also a scalar quantity. Okay, so you cannot say the mass of the body is 90 kilograms waste. No, there is no need to attach direction to the mass of the body. You can't say the time is 5 o'clock p.m. north or west. No, it is 5 o'clock, or the time taken to cover a certain distance is 5 minutes. Okay, 5 minutes is enough. No need to attach direction to it. So mass, time, and the temperature are the common examples of scalars in physics. But also speed is another example. Speed, remember, speed is the rate of change of distance, or distance covered per unit time. So distance covered per unit time is also a scalar quantity. Why is it a scalar quantity? It's because it is fully and sufficiently defined by its magnitude. Okay, so a scalar quantity has magnitude only. There is no need to attach direction to it. Okay, so real world use of scalar quantities. We use scalar quantities every day. All right, for example, you are counting money, how much money you have. All right, so you can count money. If you have 100,000 kwacha or $100, you can count 1, 2, 3 up to 100. Okay, without attaching direction to it. Okay, for example, if you go to the market, you want to buy yourself rice, for example, you can ask for an amount of rice equivalent to the money you have, and you are prepared to pay, let's say 2 kgs of rice. Okay, so the instrument that is measuring that mass will not need to specify the direction of the quantity of rice you are buying. Okay, so we use scalars quite a lot. Scalars are crucial in calculations. They simplify many everyday situations. Okay, we deal with numbers, adding numbers. You go to the hospital for maybe a medical checkup where they measure, determine your body temperature. Okay, check if you have fever. They will use a thermometer to measure your body temperature without minding the direction. Okay, so direction is not that quite important. So everyday addition, subtraction of things is basically an application of scalar quantities in everyday usage. All right. So, what are we saying? We are saying that a scalar is fully defined by its magnitude. Okay, scalar quantity is fully defined by its magnitude. Scalars do not have direction. Examples are mass, time, and temperature. Okay, but speed also is another example. You can think of other examples such as the volume of water in a measuring cylinder and many other quantities you can think of in physics are scalar quantities. All right, so having looked at scalar quantities, let's look at vector quantities, exploring vector quantities. Unlike scalar quantities, vector quantities have magnitude and direction. So we define vector quantity as any physical quantity which has magnitude and direction. Okay, so vectors combine both magnitude and direction. Okay, so they provide a more complete description. Unlike scalar quantities are only defined in terms of the magnitude, their sizes. But vector quantities, apart from having magnitude, they also have direction associated with them. Okay, so they provide a more complete description. In case they ask you in an exam to state the difference between a vector quantity and scalar quantity, you would say a scalar quantity has magnitude only, while a vector quantity has both magnitude and direction. Examples of vector quantities. Okay, the common examples include displacement. Remember, displacement is distance covered in a specific direction. Velocity, which is the rate of change of displacement. Acceleration, which is the rate of change of velocity. Force, and the others are all vector quantities. Okay, so as an examination tip, you should be able to know all these examples so that in an exam, you can give any two when they want you to. Okay, so examples of vectors include displacement, velocity, acceleration, force. Make sure you know the definitions of these terms and the context in which they are used. When it comes to representing vectors, we use arrows to represent the direction, and the length of the arrow shows the magnitude or how big the vector quantity is. So the longer the line, the bigger in representation, the bigger would be the magnitude of the vector quantity. So we are saying you can use a line like this, but at the end of it you put an arrow. So the length of the line will actually depict the magnitude of the vector, while the arrow indicates the direction in which that vector is headed. Okay, that's very important. So what are we saying? We are saying that a vector has magnitude and direction. Vectors combine magnitude with direction. Okay, that's what makes vectors different from scalar quantities, the direction property of it. So they provide more details compared to scalar quantities. Examples include displacement, velocity, acceleration, force, and the others. All right. In order to represent a vector, we simply use a line segment and an arrow attached to it. Okay, so the arrow indicates the direction in which the quantity is headed, and the size of the length represents the magnitude of the vector. I hope so far so good. So let us look at the comparison between vectors and the scalars. Okay. All right. So we just mentioned that a scalar quantity has magnitude only, while a vector quantity has magnitude and the direction. Okay. A scalar quantity can be represented by a number and of course a unit. Okay. But a vector quantity is represented by an arrow and a line segment, of course. All right. When it comes to addition, scalar quantities can simply be added algebraically. For example, you can have 2 kgs added to 3 kgs of something, 3 kgs, 2 kgs of a quantity added to maybe 3 kgs or 5 kgs of the same quantity, it will produce 7 kgs. Okay, that's a scalar quantity like mass. But vector quantities, when you are adding, you consider not just magnitude, you also consider direction. All right, you also consider direction. Examples of scalars are mass and time, while examples of vectors are force and velocity. So now make sure you know these contractions or differences between vectors and the scalars. All right, so in order to add the vectors, okay, let's look at mastering vector operations. Okay, so vectors can be added in different ways. Okay, the key areas to master when it comes to handling vectors is to know how the vectors are added, okay, and how vectors can be resolved into components. Okay, so vectors can be added graphically, in which the tip of one vector is joined to the tail of the other vector. We call this tip to tail method. Okay, what does this mean? Let's say we have vector A and vector B, right? So we want this to be added up. So we are saying that the tip of one vector, let's say A, is joined to the tail of, the tip is this part here. So this is joined to the tail of vector B, like that. The sum of these two vectors is another vector that closes the sum of these two vectors is another vector or the side which completes this triangle here. Okay, you don't just add them like you do 2 mangoes plus 2 mangoes makes 4 mangoes. No, you have to be careful. So one way to add the two vectors is to arrange the vectors in such a way that the tip of one vector is joined to the tail of another vector, so that the triangle that completes, as the side which completes a triangle represents the sum of those two vectors A and B. Okay. Another method to add vectors is to use what is called the parallelogram rule. So parallelogram rule or parallelogram method is also another approach. Let's suppose that we have a vector such as this, and another vector such as this one. Let's call this vector A, this vector B. Okay, so we want to add A to B. So how do we add them up? So for you to do that, all you need is to complete a parallelogram. So remember that a parallelogram has opposite sides equal and parallel, and that opposite angles are also equal to each other. Alright, so for vector A, you draw another line which is parallel to it. Let's say this one. And you draw another line which is parallel to B. Alright, so the diagonal of this parallelogram represents the sum of A and B. So you can call it C. Vector C is equal to vector A added to vector B. This is called the parallelogram rule. Okay, parallelogram rule. It's an easier way to add vectors. So if this is C, then C is equal to A plus B. Take note that this method is used when the two vectors are touching each other at their tails. So we have the two vectors meeting at that point, so that acting at that point, so that you by completing the parallelogram, the diagonal of that parallelogram is going to give you the sum of the two vectors. All right, that's very important to note. But also another operation is finding vector components, x and y components, to simplify calculations. Let's suppose that we have a vector. Let's say we have a vector like this. Suppose we have a vector that is represented by this line here. Suppose we have a vector that is represented by this line here, like this. Okay? And we want to resolve it into components. Components are the vectors which were added in order to find this vector. Alright, so there are usually two components. A vector has two components. Namely, it has what is called x component. So the x component acts in the x direction at a certain angle, theta. Okay? And the y component acts in the vertical component, in the vertical direction, like a y axis. So this is y and this is x. So to find x, all you have to do is apply a trigonometric ratio. Okay? Suppose you complete something like a right angled triangle which contains an angle theta. Alright? So x component, if it is a force, let's say it is a force in the x direction, all you have to do is take the vector. Let's say this vector is F for force. You simply take the vector or the force multiplied by the cosine of angle theta. Okay. Remember, this is just the introduction to the topic of vectors and scalars. Right? All right. While the vector in the y-axis will simply be, it will be force multiplied by the sine of angle theta. So f cos theta and f sin theta are called components of the vector f. Okay, we'll look at the details of this when we start looking at the more serious examples. Alright, so once again, my name is Mr. Pochilola. In case you have questions, don't hesitate to contact me so that we can address the situation. Okay, so vectors can be multiplied by scalar quantities. Okay, you can take a scalar multiplied by a vector. When you take a scalar, a number, multiplied by a vector, its magnitude of the vector is going to change. Okay, so we are saying a vector can be multiplied by a scalar quantity. We call it scalar multiplication. So what scalar multiplication does is it changes the magnitude of the vector, but the direction stays the same. Alright, so we are saying that when a vector is multiplied by a number, a scalar is just a number like 2, 3, minus 1, half, 3/4, and so on. So take a vector in a particular direction and multiply it by a number. You're going to produce a vector whose magnitude is going to be different unless the scalar is just 1 or unit. Yeah. Let's say you multiply a vector by 2. It means that the magnitude is going to be twice as big as the original one. Or if you multiply a vector by 5, it means the new vector is going to be 5 times bigger than the original vector. Okay. Okay. So a vector, when you multiply a vector by a scalar quantity, multiplication will simply change the vector's magnitude or length. For example, doubling force is a great example. Having velocity is another, like reducing the vector by half. It's also another example of scalar multiplication. or doubling a force. You push a body with a certain force, and then you increase the force so that the force is double the size of the original. Then that is also going to change the magnitude of the force. So doubling a force is another example, and also reducing velocity is yet a beautiful example. So vectors can be multiplied by numbers in order to simply change their magnitudes. All right. Okay, so what are the scalars and vectors in action in everyday life? Okay, so vectors can be used to determine direction and the magnitude of travel. Let's say you're traveling and you're flying a plane, for example. Flying a plane means you are countering other forces like air resistance and maybe gravity. Okay, so but nonetheless, you still have to fly to the set destination. Okay, so vectors can help you determine the direction and magnitude of your travel as you're flying a plane. Okay. Another example is the usage of vectors and scalars in mechanics. We use force diagrams in mechanics. Okay, so mechanics is just a branch of physics that deals with forces and motion. Okay, so mechanics uses force diagrams a lot. That's one application of vectors. But also in weather forecasting, wind vectors are very essential in weather predictions. Okay, so the direction of wind is an application of vectors. Okay, but also vectors are actually of crucial importance for safe construction in engineering. So you have to consider the forces acting on the particular bodies and the effect those forces would have on the mechanical structure of the bodies. So vectors are applied to a large extent in such situations. So to wrap it up, on scalars and the vectors, we've looked at key differences. We are saying magnitude versus magnitude plus direction is the core difference between scalars and the vectors. So vectors have magnitude and direction, but scalars have only magnitude. Okay, when it comes to solving problems, direction is very, very important when you're dealing with vectors. But when adding numbers, scalars, there's no need to consider direction. All right, so thank you very much for your attention. It has been a pleasure introducing you to this topic, very interesting topic. I hope to meet you again in another session where we're going to look at examples of involving vector addition and vector subtraction, vector multiplication with the scalar quantities. My name once again is Mr. Pochilola. Expecting to see you again next time. Bye-bye.